Alright guys, so just sort of a quick overview first of all. We'll look at forces, fields. Forces and fields are very similar, but though within electric fields we're going to have a couple of different topics, like we'll deal with field lines, and we started getting into a little bit in the class, and if you're in the online section you may have already seen that as well. Forces, fields, and then also potential. Alright. A couple things. This is a vector quantity. We find the magnitude, F equals K Q over R squared. Right, that's how we calculate the magnitude. That K is our Coulomb's constant. Fields is also a vector quantity. We find the magnitude of this electric field as KQ over R squared. So if we're just asked to calculate the magnetic field, or the electric field, that's how we do it. But also this, the force, or the electric field rather, is further defined as the force over Q. So that's where this expression comes from, this KQ over R squared. Because if we take our force right here and divide it by Q, then we're left with this KQ over R squared. So there's a couple different things that are relevant here. And out of the second expression, as we'll see in some problems, we can find, or we say that the force then of a charge in an electric field is Q times E. So if you have a charge that sits inside an electric field, it's going to feel a force that's equal to Q times E. Now, we'll show you some problems as come along with that. And then also, since now we're dealing with forces, we'll see some kinematic stuff as well.
Something like E equals F over Q. I mean, B equals K times Q over R squared. You said you're dividing by Q, right?
Right.
Is it by Q1 or Q2, or does it not matter?
It doesn't matter. Actually, this Q that we're talking about, and this is just the definition of the electric field, this Q is actually an imaginary charge, right? It's just something that you use to sample the electric field. And so when we write this out, our force then is the force between some charge Q and then some imaginary test charge divided by R squared. And then if we want to know E, we say this force divided by Q naught, and it cancels out. That's not terribly important right now. Like for just practical purposes, we need to know that we can find our magnitude of the electric field due to a charge is KQ over R squared. And then if we have a charge that sits inside an electric field, the force of the field is equal to that charge times the electric field. I'll show you an example in just a few minutes. Okay? Now, for the directions of both of these, since they're vectors, I know they didn't fully answer your question, but I think we'll see it in more practical terms in just a bit. So to find the direction, because this is a vector, for the forces like we did last time, we just go with this idea that like charges repel. Alright, and then that tells us what the direction is. So for example, if I have two positive charges, they're going to be repelled from one another. And then similarly, the opposite charges do what? They attract to one another. And so you can use that idea to figure out the direction. Now with the fields, it's a little bit more complicated. If we have a charge here, let's say that it's plus 1 nanocoulombs. And I want to know the electric field at a point that is, I don't know, 1 meter from that 1 nanocoulomb charge. To find the magnitude, I would say E is equal to KQ over R squared. So that's going to be 9 times 10 to the 9th. That's our K, our Coulomb's constant. 1 times 10 to the minus 9 coulombs divided by 1 meter squared. And 1 squared is just 1. So these cancel. That just gives me 9. And then the units for this are newtons per coulomb. Alright, so that's how I calculate the magnitude of my electric field. I just say KQ over R squared. Okay, you with me so far? Well, I'll show you some examples on old tests in just a few minutes. But certainly, you can see a question where I just ask you, what is the electric field? But then if I want to know the direction, if I want to know the direction of the electric field at that point, I imagine that I take a positive charge and I place it right here. And then I ask myself, what is the direction of the force? Is the force towards or away from this charge? If I put a positive charge right here, what is the direction of force? Towards or away? Away, because they're like charges and they repel. So the direction of the force is away, and so the direction of the electric field is away. This comes about from our definition. The electric field is defined by the force. So whatever the direction of the force is on this positive test charge is the direction of the electric field. So if I have a positive charge, the direction of the electric field at that point is in that direction. All right, so that's how we find the direction. To find the direction, you ask, what is the direction of the force on our positive test charge, Q naught, which again is an imaginary test charge. It doesn't have a magnitude, it doesn't have a charge, it's just something that we use to imagine, to sample what is the electric field. Alrighty? Okay, so that's electric field. Now, potential is something that we haven't gotten into yet. Let me show you, just sort of to list it here for completion because it follows closely. Let me first show you, if I take this charge and I map out the electric field, and we'll look at some lines in just a bit, but if I map out the electric field, I represent it with electric field lines like this. All right, those are electric field lines around this positive charge, and they just represent the direction and the magnitude of the electric field. I'll show you some questions in just a bit on old tests regarding this, but just be with me for now, stay with me for now. Now, if I imagine that I have a charge along these, if I move it to this point, and then I move it around the circle, there is no force required to move it from here to here. Now, if I move a charge from here to here, it requires a force, because the force increases when I go from here to here. But if I move it along this point, from here to here, then it doesn't require any force. Right? It's like taking, we talked about this last semester, but it's like picking up an object and then just moving it around from side to side. I'm not doing any work on the object because it doesn't require a force to move in that direction. It requires a force to pick it up, and I do work in that way. But to move it around at an equidistant from the surface of the Earth doesn't require force. So I can draw then these lines, which if you're in lab, you've already mapped these out. Did y'all do these? Yeah, these are called equal potential lines. And the equal potential lines are just lines where the potential is equal all the time. And so the potential is first a scalar quantity. So it only has a magnitude. We calculate that magnitude, KQ over R. We're not going to get into how it's derived, but it actually is derived from this electric field. So it all goes back to that Coulombic force. You have to take the derivative of, or the integral rather. And then KQ over R, let's see, oh, this is, in just very basic terms, the potential is energy per unit charge. All right? Okay, so those are sort of the three big ideas that we're going to have on the test. We'll have forces, in which case you'll have some vector problems like we did last time, either 2D or 1D vectors. We'll have field problems where likewise you'll have to do maybe some vector problems, 2D or 1D. You might also have some kinematics problems where you measure that force and then you figure out what is the velocity or the displacement after a certain amount of time. Also within the fields, you have to be able to interpret the field lines, which we'll go into in just a bit. And then the final idea is potential. By the way, this is going to be the same potential that we'll talk about with voltage, like for a power supply or the voltage that you have out of your outlet. It's the same idea. It's a measure of energy per unit charge. So potential is a scalar quantity. Potential is the magnitude is equal to kq over r, and it's just a measure of our energy per charge. Okay, let's do a quick fields problem. Let's say that I have two charges. This is very similar to what we did last time with the forces, but I think the vectors are often difficult, so we'll just do it quickly here. So let's say that I have two charges. I have one charge that is 1 microcoulomb. I have another charge that is 2 microcoulombs, and I want to know what is the electric field at this point. I'll need to give you some distances. Let's see, I'll just call this 3 meters. I'll call this 4 meters. And I want to know the electric field. All right, I'll call this charge number 1 and this charge number 2. Okay, so in order to do this, first I want to, actually let's make one of these negative. I'm going to make this 2 microcoulomb charge a negative 2 microcoulomb charge. First I want to label my vectors. Okay, so the electric field due to this charge, I imagine a positive charge right here, and I ask myself, what would be the direction of the force that it would feel? It would feel a force that would be repulsive. And so E1 is in that direction. And then E2, I put a positive test charge there, and I ask, what would be the direction of the force due to this charge? Attractive or repulsive? It's an attractive force, so that's going to be E2. All right. Then I'll need to, I can go ahead and draw my axes there. So there's my coordinate system, and I need to define what is this angle. But notice I have a triangle here. That angle turns out to be 37 degrees. You can do the inverse tan of 3 over 4 to find that angle. You with me in this? No? Is this, you want to go through the vector stuff, or you want to go into other things? Huh? Okay, why don't we go on to other things, because we've done very similar problems to this. Once you get to this point, then all that you have to do is calculate E1. E1 is going to be K times 1 times 10 to the minus 6 coulombs divided by R squared, which is 4 meters squared. So that's how you find the magnitude. And then you do a similar thing for E2, where E2 is going to be 2 microcoulombs times K over 5 meters squared, which is this distance. So these problems from this point on, they work out exactly like the Coulomb's law problems. Let's go on though, because there are homework questions that deal with that, and then there are old test questions as well. But let's look at the fields as well. But you can very much see a question like that, where I just ask you, what is the net electric field? Show you another question that you could see. Let's say that I have a charge. I have a charge that is 2 nanocoulombs, and then I place another charge. No, I'm sorry. Well, first, yeah, let's just say, what is the electric field at this point? Let's say this is 6 meters away. All right. So my electric field then is kq over r squared. That's 9 times 10 to the 9th. Q is 2 times 10 to the minus 9. So those cancel. Divided by 6 meters squared. So that's 1/2 Newton per coulomb. Right, so my electric field there has a magnitude of 1/2 a Newton per Coulomb. And then we might ask, what if we put a charge of, say, I don't know, 2 coulombs at that point? What force does it feel? In which case we go to this idea that the force is equal to Q times the electric field. Q is 2 coulombs. That's just the charge. So we're placing a 2 coulomb charge at that point, and I want to know what force does it feel. Times the electric field, which is 1/2 Newton per Coulomb. So it feels a force of 1 Newton at that point. And then we could go on and ask, well, let's say this was, I don't know, let's say it had a mass of 2 kilograms. So if the particle what is the acceleration? All right, that goes back to our Newton's second law, F equals ma, or A equals F over m. So we have 1 Newton over 2 kilograms, which is, 1/2 meter per second squared. And then from that, I could ask, what is the velocity after 2 seconds or so? What would be the velocity after 2 seconds? I have an acceleration of 1/2 meter per second squared. Okay, we go back to your kinematics equations. Say V is equal to V naught plus AT. A is V naught is 0. A is 1/2. If t is 2 seconds, then my velocity is just 1 meter per second. Or similarly, you could also ask, what is the displacement, say the x displacement after 2 seconds, in which you'd say it's just 1/2 AT squared. So that would be 1/2 of 1/2 meter per second squared times 2 seconds squared is 1 meter. Basic kinematics, stuff like that. Just you need to know the equations. There's nothing going to be terribly complicated. Just sort of one-step kinematics problems, finding the final velocity or the displacement. All right. All right. So those are sort of basic field questions. Something that you'll see with regards to potential is finding the potential of multiple particles. Can I go on for minutes? You okay with this? Feel okay? All right, in just a couple minutes, we'll look at some old tests. Let me go over this idea, and then we'll look at the old test. Can I go to the next page? No? Oh, wait. Okay. Guys, if I'm going too fast, please just stop me, okay? I'm okay going back and going over ideas. All right? With me? With me, sort of? All right. All right, let's look at a collection of particles. So the potential of a collection of particles. Right, so this would be similar to finding the electric field like we did with the 2-particle system, but it's a heck of a lot easier. That should be potential, I'm sorry. It's a heck of a lot easier because electric potential is a scalar quantity, not a vector quantity. So when you add up potential, you just add it up like numbers, not like vectors. So let's say that I have, I have 4 charges. Let's say that I have 1 nanocoulomb, 2 nanocoulombs, -2 nanocoulombs, and 3 nanocoulombs. And these are all situated on a square that is 10 centimeters on side. And I want to know what is the potential at a point right in the middle. our potential, if we want to calculate the potential due to an individual charge, it's just going to be V equals KQ over R. So what I want to do here is find the potential, the energy per unit charge at this point due to each of these individual charges, and then just add them all up. So the total potential, I'll call this particle number 1, 2, 3, and 4. The total potential will equal V1 plus V2 plus V3 plus V4. Now, I know I can simplify this particular problem out. A couple of these terms I can just get rid of. How is that? Which ones can I get rid of? 2 and 4 can go away because I have two opposing charges. These two charges, one is positive and one is negative, and they're a distance that is equal from the point that I'm considering. I want to find the total potential at this point. This charge contributes a potential, and then this charge contributes a potential that's exactly opposite. So I can just cancel those out. So I'm going to get rid of these two. And you know, often in problems when I give them on tests, there will be some little trick like that. Now you can go through and calculate it all, but it'll save you a lot of time if you recognize right off that because of symmetry and the charges being opposite, that V2 and V4 go away. So V2 goes away, V4 goes away, and I'm left just with V1 and V3. All right, so at that point, I need to know what is this distance, and then similarly, what is this distance? Those will be the same distances. One is half the other. If I draw that, that's a triangle. I have 0.1 meters, that's 10 centimeters. 0.1 meters there. And what's that? I think it's 0.07. 0.14 meters. So this distance is 0.14 meters. That means that this distance is 0.07 meters, and this is 0.07 meters. See the triangle I drew there? What's a trig in this chapter? So if you're not up on your trig functions and your quadratic function, or your Pythagorean theorem, rather, I don't think that. All right. So now I can calculate the potential for each of these. So V1 is going to equal 9 times 10 to the 9th times 1 times 10 to the 9th, minus 9 rather, divided by 0.07 meters. Not squared, it's not squared. And then V3 is going to be 9 times 10 to the 9th, 3 times 10 to the minus 9, divided by 0.07. Right? I could factor out that 9e to the 9th divided by 0.07. Makes your calculations a little bit easier. I divide that out, and then I factor it all out, and then I just add 1 plus 3 times 10 to the 9th, which is 4. Minus 9. However you want to do it, but I get 500 volts here, 514 volts. 500, keeping proper sig figs. You might make that easier just in your calculations. You can cancel out these 10 to the 9th, 10 to the minus 9s. So you're left with 9 over 0.07 plus 27 over 0.07, and that gives us 514. I try to give you all nice, easy round numbers, so it just makes the calculating easier with your calculator. All right. Let's look at some old tests. Is that useful for you? Some old questions on tests. But this is sort of the rough idea, or not the rough idea, but the idea behind finding the potential due to collections of charges. And we'll see why that's important later. I don't know if we'll get into it today. But you do need to know just sort of the mechanics of how to do that, finding the potential due to collections of charges. All right, let's see. 12, spring 13. Have y'all been doing the quizzes okay? Are they helpful or just a pain in the rear? Are they helpful? It's okay if they're not. You can tell me.
Helpful, I just wish, like, some problems I don't know, like, what I'm doing wrong, but there's, like, no explanation on how
I
to do
understand.
it.
I'm sorry. That's not forthcoming.
Yeah.
They are old tests. Like all those questions are from old tests. So if you really want to mine down into the old tests, the solutions are there somewhere. But I think a lot of people just put that off until the very end, like going through those questions. So it's really for those people to help them. I know you're not that kind of person, but some people are. So all right. Let's see. Okay, let's look at some of these electric field problems. By the way, this is last spring's test, if you're keeping up with that. Let's look at this one. This one is actually from a homework problem that you had. I have a -1 nanocoulomb charge that floats in an electric field. The only forces on the charge are from gravity and the electric field, and the mass of the charge is that 1 × 10⁻⁹. What is the magnitude and direction of the electric field? So if I have this charge, I know that I have the gravitational force, which is down, and if it's floating, that means it's just stationary there, then that means that the electric force has to be up. So the gravitational force is down and the electric force is up. So first, oh, and this is a negative charge, -1 nanocoulomb charge. First, we want to ask ourselves, what is the direction of the electric field? Positive charges feel forces in the direction of the electric field. I've already said that. Wait, say it again. Positive charges feel a force that's in the direction of the electric field. So what must be the direction of this electric field for this negative charge in order to produce a force that is directed upward? What is the direction of the electric field?
Negative.
Up or down? What do you think, Craig? You were right. Yeah, it is down. So positive charges feel a force that's in the direction the same as the electric field. All right, so if this was a positive charge, the electric field would be in this direction, the same as the force. But since this is a negative charge, that means that it's sitting inside of an electric field that is going down. All right, so immediately we can get rid of this answer and this answer. All right, now I want to know what is the magnitude of this electric field. Since it's floating, there's no acceleration, then I can say the sum of the forces equals 0. That means that I can say the magnitude of the electric field is equal to the magnitude of the weight. All right, so this is kq over r squared. I'm sorry, not kq over r squared. F is equal to QE. That comes about from our definition of the electric field. And this is equal to m times g. And now I'm trying to solve for E. So it's just mg over q. M was 1 × 10⁻⁹ kilograms. This is 10. And q is 1 × 10⁻⁹ coulombs. This was kilograms. And notice that these numbers cancel, so I'm left just with 10. So it must be C, 10 newtons per coulomb downwards. So a couple steps here. I first had to determine the direction of the electric field, because you notice if you had found 10, you might have also said A, which was upwards, but that's not the right answer. It's downwards because it's a negative charge, And the force due to the electric field has to be up in order to counterbalance the gravitational force. And a negative charge feels a force that's in the opposite direction of the electric field. That comes out of our definition of the electric field. So those type of problems that you'll see for electric field type things and that definition of our electric field. Can I clear this, y'all? Let's see what else we got here. Here's another one. This one's pretty simple, but you could see something like this. I have a proton that's 3 meters from a 1 nanocoulomb charge. What acceleration does it experience? Right. A couple things you could do here. Probably the easiest thing would just be to use your Coulomb's law to find the force that it experiences, and then figure out the acceleration by just F over m. So Coulomb's law is KQQ over R squared. That's going to be 9 times 10 to the 9th. Q of a proton is 1.6 times 10 to the minus 19. And Q is 1 times 10 to the minus 9 divided by 3 meters squared. I can cancel out some numbers here. That cancels there with that. This cancels with that. And I'm left with an acceleration of 1.6 times 10 to the minus 19. That 1.6 times 10 to the minus 19, that's a good number to know, just because, you know, it's the fundamental unit of charge. But it's on your equation sheet, so you don't have to know it. None of the constants you have to know, like all the masses of your proton, electron, all that business, those are all on your equation sheet. Then you want to know the acceleration, F over m. I'm sorry, this was not meters per second squared, this should be newtons, right? It's the force. So that's going to be 1.6 times 10 to the minus 19 divided by the mass of a proton. You don't have to know, but it's 1.67 times 10 to the minus 27 kilograms. This was newtons. And then let's see, if we divide those two, looks like B is going to be the right answer. 100 million. I can just look at this. I can basically cancel out these two coefficients or whatever. And then 10 to the minus 19 over 10 to the minus 27 is 10 to the positive 8. So it's 100 million. 1 times 10 to the 8. Basic kinematic stuff with the electric fields, but you'll certainly see one or two. I mean, here we had a couple of those problems, these that we've seen here. All right. Let's go on to some potential problems. Can I clear this? Okay, here's just a basic potential problem. I have two charges, and I want to know the potential at point A. All right, so like if this was a field problem, you'd have to go through all the vector business. You'd have to draw your vectors, and you'd have to find the magnitude of the vectors, and the direction of the vectors, and then the x and y components, and add the x and y components, and then use the Pythagorean theorem and the inverse tangent to do all that business. But here it's a lot easier. I just say, all right, at this point, I have two potentials. My potential is going to equal, I'll call this charge 1, charge 2, is going to equal potential due to charge 1 plus the potential due to charge 2. That's going to be K, which is 9 times 10 to the 9th, Q, which is 9 times 10 to the minus 9, divided by R here, which is 3 meters. So V is KQ over R. That's on your equation sheet. Plus, I'm going to write it down below here. I'm going to run out of room. 9 times 10 to the 9th minus 4 times 10 to the minus 9 divided by 2 meters. Notice here, unlike I did for electric fields, when you have potentials, you always include the sign. This is because when you're dealing with electric fields and electric forces, you don't include the signs because you already accounted for them when you drew the vectors. Remember, because we we figured out what was the direction of the vector irregardless, and then later when we calculate the magnitude, we don't include the sign. Yes? Remember that? Don't include the signs when you're doing force and fields. But when you're doing potentials, you do include the sign. So this negative 4 nanocoulomb charge has a negative potential.
So since it's just like the other one, will it be, will they like put it on the same, but is it potential? Like how will you know?
I'll say potential, like as versus the field.
Yes.
Yeah, you'll know because, well, first of all, I'll ask for potential. I won't ask for magnitude or direction. And then the others, I'll likely have, you know, a couple problems that follow one after the other. One asking for the magnitude and one asking for the potential, for the direction. And then also, if you just look at the units as well, the units are in volts. So, I know it looks very similar, but you have to read them carefully. And also, it'll come later in the test, because as you know, I lay out the test by chapter, and potentials are in chapter 2 and fields are in chapter 1. All right? So, there'll be a progression from forces to fields to potentials. All right, if I do these, the numbers add up nicely. These cancel, these cancel. But again, I try to have these work out nicely. So this is, the top is, this cancels and leaves a 3, gives me 27. That cancels and leaves a 2, minus 18, and that's equal to 9 volts. Be careful though, because if you don't include this negative right here, 27 plus 18 is 45. So if you don't include that negative, that's a common mistake that students make, then you'll get the incorrect answer, but it'll be there. Alright? Some other common mistakes, which are accounted for in these other answers, or another common mistake is if you square this. But potential is KQ over R, not KQ over R squared. So we have these three big ideas, okay? Force, KQQ over R squared, fields, KQ over R squared, and then potential KQ over R. It's this sort of progression as we go from one to the other. And as we go from forces to fields to potential, you're sort of losing a variable as you go along. You lose a Q and then you lose an R. Alrighty? Just a few more minutes. I know it's... Can I take this away? Alright. Let's look at this one. We're going to get into this in the concept test, or if you're in the online section, you'll see it in the online quiz. What are we calling that? The OT quiz now. Is that what we're calling it? Oh, Corinne, you're yeah, so you'll see this in the OT quiz. Where on this line is the potential equal to 0? In this, remember, when that previous problem where we had the charges canceled out the potential because they were a positive and negative charge that were equidistant from a different point? There are points on this line where the potential is 0. So say, for example, I take this point. It turns out that B is the right answer. But if I take this point is a certain distance from that charge that is equal to the distance from that charge. So the potentials of those two charges will cancel out because R is the same and Q is the same but opposite. So one has a positive potential and one has a negative potential. Similarly, the distance from that charge and that charge, those are the same. And they have positive and negative charges, so they're going to cancel out. And then likewise, the distance from here to this charge and the distance from here to that charge, those are the same. So the potentials due to those two charges will cancel out. So the total potential at that point is equal to 0. Right? So it turns out actually if you put a charge there, it'll just sit right there. It won't move. It doesn't change energy. It's at its lowest energy at that point. So let's look at some of these other positions. Like say, for example, I took this point. Now at this point, these two charges cancel out because their distances are the same and you have opposite charges. But look, the distance to that charge and the distance to that charge are different. So that means that due to this charge and this charge, I have a net negative potential. Because the negative charge is closer. Wait, no, is that right? Yeah, the negative charge is closer, so it contributes to potential more. R is smaller, so V is bigger. That negative V is larger. So it doesn't cancel out, is the point. And the same with the 2 coulomb charges. This distance is different from this distance, so they don't cancel out. Again, we'll see that in the online quizzes or the concept tests that we do in class. Can we do one more, y'all? Is that okay? I want to get out of here in just a couple minutes, but while we're here. Okay. I have this collection of charges. Again, another type problem that we'll see. And I want to know what is the potential and the electric field at the center of this square. Not numerically, just qualitatively. Is the electric field 0, or is it not 0? Is the potential 0, or is it not 0? Now you should be able to look at it right away and tell me, is the potential at point P, is it 0 or not 0? The potential, which remember is a scalar quantity. 0 or not? It would be 0, right? Because I have the potential due to this charge cancels with this charge because it's equidistant from that point P, and these two charges also cancel out. Or I could say these two charges, they cancel out their potentials, and these two charges cancel out their potentials. But the end result is that the net potential, the total potential, is equal to 0. To find the electric field, whether or not it's 0, is a little more complicated. If I imagine this charge, the electric field, remember I place a positive charge here and ask myself what is the direction. The electric field due to that charge is in that direction. The electric field due to this charge is in this direction. The electric field due to this charge is in this direction, and then the electric field due to this charge is in that direction. So is the electric field equal to 0? No. What would it look like if the electric field were 0? How would those vectors look different if the electric field was 0? Right, they would all be canceling out. So if it were 0, and you can arrange these charges so it is 0, the electric field vectors would all look like this, so that they'd all cancel out one another. But in this case, they're not canceled out. All right, so the potential is 0, the electric field is not 0. All right, well, I think we'll stop there. But next week, we'll meet again. We'll do potential. And, we'll be getting close to the exam, I guess. When is the exam coming? What is next week? So is that next Monday? Not this Monday, but the next Monday? Okay, yeah. So potential is definitely going to be on that exam. But not the second part of chapter 2. So not capacitance, which is in the second part of chapter 2, but potential will be on that exam. So these things, this is most of the material that's on the exam that's coming up. There's still 1 or 2 things that we haven't done. Potential energy we haven't looked at. But it's very closely related to potential.
So for the most part, I can go like practice the exam once a day?
Absolutely, yeah. You can go ahead and take a look at exam 1. Our chapters 1 and 2A, which is the part about potential. If you see anything about capacitance, that's not on the exam. I don't usually get to that on exam 1 anyway, so. All right, y'all.